So the goal of today is we're going to take these terms and the definitions of the principles that we've talked about, including transgressions and regressions, and talk about how you can use these concepts to map out geologic histories of given cross-sections. So the process would be, I give you a cross-section, you look at that cross-section and tell me as a sequence of ordered steps the geologic history of what happened in that particular region. And you're going to be doing this on paper at first today, pretty simple. What we're going to be doing on the Shoal Creek field trip is going out to a really famous cross-section in Austin and doing this real-time, looking at the rock layers with our faces, interacting with them, doing some chemical tests and stuff like that to be able to ascertain what types of rocks they are and then mapping out a geologic history from there. What a geologic history consists of is denoted on this slide, and it's also, if you want to flip your page over, denoted in the paragraph at the top of that page. What this is really a sequence of numbered steps ordered from oldest to youngest that lists formations of rock layers, deformations of rock layers, periods of erosion. As we talked about, those would be evidenced by unconformities, both disconformities and angular unconformities, faults, igneous intrusions or crosscuts, river crosscuts, things that are exemplifying the principle of cross-cutting relationships, sea level changes, okay, this can be exemplified by regressions and transgressions, and if you can, geologic time periods and dates. So as much information as you can possibly give from a particular cross-section regarding the history, again as a series of numbered steps. So take a look at that first cross-section that I've given you on the back page. It's the first cross-section, I guess, the top diagram. What I want you to do is work with members at your table and come up with a series of numbered steps that best depicts the geologic history of this area. You might notice that there are a lot of things on here. There are symbols for limestone, sandstone, and shale throughout. Those are the only symbols that I use. There's also some nice evidences of erosion and sea levels rising and falling and stuff like that. I want you to do the best you can. I'm asking the sub to give you 8 total minutes to complete this as a group, and then we'll see how well you did. So we're going to pause this now. I want you to try your best to give me a series of numbered steps representing the geologic history of this cross-section. So go ahead and pause it. 8 minutes. I'm hoping you paused it for 8 minutes. If you didn't, here's another chance to pause it for 8 minutes. Pause it for 8 minutes. So, I'm hoping by this point every group has a series of numbered steps, and you might have no clue what's going on at this point, and I think this review will really help you map it out. But you need to pay attention and relate this review to what you already have written. So what I want you to do is get out a different color of pen or pencil and make corrections on your geologic history. And this is not going to affect your grade. If you complete this assignment, you're going to get 100. Great, fine. But I do want you to denote the difference between what you originally had and what you're modifying based on the review. So go ahead and get out a different color of pen or pencil. So let's go ahead and review this. Looking at this cross-section, I see layers that are labeled 1, 2, 3, 4, 5, 6, 7, 8, etc. Cool. So we're going to start with 1. We think that layer 1 is the oldest rock layer. Great. Remember that rocks are originally deposited horizontally. So you might notice, okay, it looks like 1 was deposited, then 2, then 3. They should have been deposited originally horizontally. So we're not going to be talking about this weird tilty thing yet, because remember the first step is horizontal deposition. What we can note, though, is that this is limestone, this is shale, this is sandstone. So this is a coarsening upward sequence. We have the smallest particle size here, medium-grained particle size here, largest particle size here, a coarsening upward sequence. So the first thing that you can note is, okay, the seas must have been above this landscape when deposition was happening. But because this is coarsening as we're going up in the rock record, the seas must have been falling. Yeah? Hoping that makes sense. So we have limestone layer 1, shale layer 2, and sandstone layer 3 deposited during a regression, i.e. deposited when the sea level was falling. I'm hoping you notice that these layers are no longer horizontal. They're in fact tilted. So that's the second step that happens. We must have had tilting of these rock layers to affect their horizontality in some way. So all layers are tilted. All layers are tilted. Again, don't need to know what specific process did that. We just know it happened. The third step is, I'm hoping you noticed this right there, that squiggly line. That is evidence of erosion. So the regression must have continued. Sea levels must have continued to fall, eventually exposing this landscape above the surface of the water to chemical physical weathering, which resulted in the erosion of the landscape. There we go. A regression exposes the layers and they are eroded. Now let's look at the rest of this. We have sandstone here, shale here, limestone here, sandstone again, limestone again. Kinda odd. So what we can diagnose from this is larger particle size, medium grained, smaller particle size. And then we go back to larger, which is kind of confusing. So at least through this deposition sequence here, we know that seas were rising. And the reason why we know seas were rising is because this is a fining upward sequence. We have large particle size down here, medium grains here, smallest grains there. So we know from here to here, really this deposition event took place when seas were rising, and that's called a transgression. So sandstone 4, shale 5, and limestone 6 are deposited during a transgression. Now let's figure this out. So we're kind of right here, and if you're looking, this is limestone and this is sandstone. So while this was a fining upward sequence, this right here is a coarsening upward sequence, going from limestone to sandstone. That's actually, our grains are getting more coarse. Okay, so now we know regression at that last part. So we have a transgression to deposit these rock layers, a regression to deposit this sandstone layer. Now let's look at this last part. This is sandstone, this is limestone. Limestone is a smaller particle size than sandstone. So this sequence is a fining upward sequence, just like the lower sequence was, this one. So this sequence is fining upward sequence, which means the seas were rising during this last deposition event. So, limestone 8 is deposited during a transgression, indicating that the seas were rising. Let's review this. So, our first step is limestone 1, shale 2, sandstone 3, deposited as the seas were falling. We then have the tilting of these rock layers from their original horizontal position. We then have continued regression, which serves to expose the landscape to erosion, as symbolized by this angular unconformity. We then have sandstone 4, shale 5, and limestone 6 deposited as the seas were rising, because that is a fining upward sequence. We then have sandstone 7 deposited as the seas were falling, because that is a coarsening upward sequence. And then lastly, we have limestone 8 deposited during a transgression, because that again is a fining upward sequence. So take a second and pause this, and if you need to discuss at your tables and make sure that you understand how this is working, definitely do so, because it's sometimes tricky stuff. Okay, so let's go ahead and move on to this next one, which is a little bit more difficult. This is kind of a challenging one. I want you to, as table groups, do exactly the same thing for this one. You're going to have 8 minutes again to do it. A couple specifics. One, for these layers here that are just white, you don't have to worry about transgressions and regressions, because I'm not giving you any information regarding what those rock types are. Secondly, this thing here, That's igneous rock. That's an igneous intrusion. So that should be all the information you need to know. You need to know to complete this second part. Again, come up with a detailed geologic history as a sequence of numbered steps that best describes how the rock was deposited and deformed in this cross section. Go ahead and pause it and get started. 8 minutes. Okay, so I'm hoping it's been 8 minutes. If not, go ahead and pause it. Make sure each group has had 8 minutes to complete this. All right, so this cross section was a little bit more difficult. There's some tricks involved in analyzing it. The first trick is, okay, we have rock layers 1, 2, 3, 4, 5, 6, and 7 over there. And then we have 10, 11, and 12. So where did 8 and 9 go? Well, they must have been there and been eroded. So our first step is layers 1 through 9 were deposited. And remember, they were originally deposited horizontally. So there we go. Layers 1 through 9 are deposited. Now, people are probably going to get pissed here because there's some other tricks that are a bit annoying. I'm assuming everybody noticed that these layers are tilted. They're no longer horizontal. They're tilted. However, what you might not have noticed is that they also don't line up horizontally even after tilting. So you can see that 3 does not line up with 3 over here. 4 does not line up with 4. 5 does not line up with 5, etc. And this is indicative of, if you guessed it, great job, a fault, specifically a dip-slip fault. So the order of this is a bit enigmatic. You might not have the order exactly as I'm about to describe, and that's okay. Just know that it can be flip-flopped a little bit, and I have no evidence to the contrary. But what I have as the next step is that faulting. So I'm saying dip-slip faulting occurs, shifting the layers in relation to each other. Okay. And obviously they're not parallel anymore, so something also has to have occurred, namely the tilting of the rock layers due to some tectonic activity. So there I've symbolized that. And I say here possibly before faulting. I have no reason to believe that tilting occurred after the faulting or before the faulting, one way or the other. Doesn't matter, and this is all made up anyway. So I'm saying here that it happened afterwards. If you put that it happened before, that's totally fine. You wouldn't get counted off on a test for it. Some of you might have also put the next step, which is this igneous intrusion cutting through all these layers. You might have put that before the faulting. You might have put it before the tilting. I actually have it as the next step. Igneous intrusion cross-cuts layers 1 through 9. I don't know if it cross-cuts layers 7, 8, and 9. I'm just assuming there's no specific direct geologic evidence that it did that on this cross-section. I also don't know for sure whether this happened after the tilting and after the faulting. I would be willing to argue with you, though, that it happened after the faulting, and here's why. So when we have faulting, let me draw a fault here. Yeah, so there's my fault in my rock. Great, cool. This area of the rock is typically very weak because it's already cracked. And so if we have a pocket of magma down here that erupts up through the Earth's surface, odds are it's going to follow that path right there and spew out, here we go, volcano action happening. Great. Odds are it's going to happen along that weakened path. And so that's why I'm strongly arguing that this igneous intrusion happens after the dip-slip faulting. Regarding the tilt, who the heck knows? You can put it as happening before or after the tilt, but I'd be willing to strongly argue that it happens after the faulting because I think that those layers are weakened. What's the next step? Well, you should have noticed this unconformity here, which is indicative of erosion. So seas must have fallen. We must have had a regression of some kind to expose this rock to erosion, and erosion must have taken off some layers. So that's what I have as the next step. A regression occurs exposing the layers, and they are eroded. Great. So let's look at these final steps. And this is actually a little bit more difficult than you might have originally thought. Layers 10, 11, and 12. 10, 11, 12. This is limestone, this is shale, this is sandstone. So clearly, this is a coarsening upward sequence. Yeah, coarsening upward sequence. So we know that the seas were falling during that upward sequence. We know that that was a regression. However, at this point in time in our history, sea levels are below the landscape because we've just had erosion occur. So we kind of have to frame this in a little bit more tricky of a way. Seas have to rise at least a little bit to start the deposition of limestone. And this could be a really quick rise because we don't have any evidence of any other types of rock in this region before the limestone. So quick rise, seas rise very quickly to deposit limestone, namely part of layer 10. And then my best guess is we have a slow falling of the sea level to deposit the rest of 10, 11, and 12. Because again, we're monitoring the sea level, right? Here, it's below the landscape. It's below the landscape there. So it has to rise to be above the landscape for deposition to happen at all. So it rises, quick rise to deposit some limestone, then it falls to deposit the rest of that coarsening upward sequence. Okay, so for this next step, I have part of layer 10 being deposited during a transgression. Remember here, our sea levels are below the landscape. We've just eroded. So in order to get rock deposited at all, seas have got to rise to be above the landscape. So hence, this transgression has to occur. So this last step, we have the rest of layer 10, all of layer 11, and all of layer 12 deposited during a regression. So again, to review, step 6, we deposited part of this guy during a transgression. Seas are now above the landscape, and then we have a slow regression, which is evidenced by this coarsening upward sequence to deposit the rest of 10, all of 11, and all of 12. And that means the seas were falling during that deposition sequence.